Good. So when is your math final?
My math final is on Monday.
Okay. So this is probably our last session before your final?
Yeah. Well, I think my mom wanted to schedule one on Saturday too, hopefully.
Okay, I can certainly do that. Saturday is going to be a blizzard or certainly cold outside. An online
Yeah.
session sounds just the thing.
Uh-huh.
So remind me before we leave, and I'll go ahead and
Yeah, I will.
schedule that one. So what are we doing tonight?
Just kind of like reviews on like problems that I'm having trouble on.
Okay, can you verbalize them?
Yes.
Okay.
Okay. So the first one is um okay. So it says write the quotient in standard form, and the quotient is 5 over 2 plus I.
Okay, so that's the quotient.
Quotient, sorry.
Okay, and when you have complex numbers in the denominator, it's a lot like having irrational numbers in the denominator. In other words, when I give you that expression, that's not really a division problem, is it?
No.
No. In other words, the way I'm going to solve this is by multiplying the top by square root of 2 and the bottom by square root of 2. And then I
Yeah.
end up with square root of 2 over 2, which is very acceptable because my irrational number is in the numerator.
Mm.
Same thing with imaginary numbers. The goal is not to actually divide that, but it's to turn the denominator into a real number. And the way
Okay.
to do that is by multiplying by the conjugate. That's the conjugate of the denominator.
Okay.
Let's multiply that out. What do we get? Let's do the denominator first. What's 2 plus I times 2 minus I?
Minus I, and so 2 times 2 equals 4, obviously. Plus 4I and minus 4I cancel out.
Well, it's plus 2I and minus
Oh, plus
2I. They
5.
cancel out, correct?
And then I times negative I equals negative I, and that just equals negative 1, right?
Well, it's negative I squared,
I squared, sorry.
Yeah.
okay? And I squared is negative 1. In other words, that's an identity. Whenever you run into an I squared, you can turn it into a real number, okay?
Okay.
So now we've got the denominator equals 5
Okay.
because 4 minus a negative 1 is 5,
Yeah.
okay? Now the numerator, just multiply distribute the 5 and you get that, okay?
Okay.
And if I move that over to there, now I can see that I can simplify that. What would that simplify to?
Um, 2 over 2 minus I over 1.
Yeah, or just 2 minus I.
2 minus I.
So there's your answer. And
Okay.
notice that that doesn't look much like that at all, and they rarely do. When
Mm-hmm.
you are, and this is a process that I like to call realifying the denominator, because we call the other process rationalizing the denominator. Well, let's call this realifying the denominator.
Okay.
And that's all we're doing.
Okay.
Now, let me just give you, if I had a number like, hold on a second, let me think, 10 minus 8I over 6. Let's say I got that as an answer.
Okay.
Standard format for complex numbers is A plus BI. That's the way you want to end up writing most complex numbers.
Okay.
In the problem you gave me, that's exactly the format we got. 2 minus I. In other words, b is minus 1.
Mm-hmm.
If I would have gotten something like that, well, that reduces to 5 minus 4I over 3. Now, if I want to put that into a plus bi format, I got to separate it into two fractions. Those two fractions right there. So the actual answer, if they wanted it in standard format, would have been that.
Okay.
In other words, always separate those two fractions apart so that you end up with a plus bi, and b is minus 4/3.
Yeah. Okay.
And a and b are always real, and b is just the coefficient of the imaginary part.
Okay.
So depending on your teacher, they might accept an answer like that. Well, they would want you to at least simplify it to 5 minus 4i over 3.
Yeah.
Whether they would want you to take it all the way down to a plus bi format, I don't know. That just kind of depends on the teacher.
Okay.
I wasn't sure if that was the kind of lemonade that
Okay.
Ellen liked.
All right. The next one is find the path of the ball given by y equals negative 1/20 x squared plus 3x plus 5.
Okay. Yep. Catch you later. Bye.
Okay, so a quadratic is a parabola, and motion is in a parabolic shape. In other words, if you threw a ball up in the air, it would come down. It would follow the path of a parabola.
Okay.
Okay? And when they said find the path, what specifically are they asking? Because usually questions like this are find the peak, find when the peak happens, and find when it hits the ground.
They want the maximum height of the ball, the number that determines the height at which the ball was thrown, and does changing this value of the coordinates of the maximum height, does this change the value of the coordinates of the maximum height of the ball?
All right, I think I understood all of that. Let me draw my picture differently, because apparently the ball was thrown from some height. So its path is going to look like that, with that being its initial height.
At 5 feet, right?
And we can call that y, but also we could call it h as a function of x, with h being height. Okay?
Okay.
So we're going to want to solve for that. But first of all, let's figure out where the height occurs. In other words, what is this point right there? And then not only where it occurs on the horizontal axis, but also what is it there? So
Okay.
we need what? The vertex of that parabola, correct?
Yeah.
Okay. So let's figure out the vertex of that parabola. We need the x-coordinate of the vertex, and we need the y-coordinate of the vertex.
Mm-hmm. Okay.
Now, there's a couple of ways to get this. We could put that in vertex format, which would involve completing the square, which is going to be a little difficult because 1/20th is the coefficient, so it's going to get a little complicated. There's actually an easier way to find out the x-coordinate of the vertex of any quadratic or parabola. Do you know what that is? Minus b over 2a.
Okay.
That gives you the x-coordinate. And in case you have difficulty knowing what that is, Let's remember what the quadratic formula is. Remember the quadratic formula?
Yes. Negative b plus or minus b squared minus 4ac all over 2a.
Right, and that b squared minus 4ac is under a radical sign also.
Yeah.
Okay.
Sorry.
So that's the quadratic formula. Well, if I take the first half of that, in other words, if I were to split that up into two fractions, like I was showing you how to do with complex numbers, then the first fraction would be minus b over 2a.
Yeah.
Okay, so if you ever forget what that formula is, it's the first half of the quadratic formula.
Okay.
Okay? Or if you ever forget what the quadratic formula is and you know what the x-coordinate of the vertex is, in other words, these kind of help you memorize each other.
Okay.
This helps you memorize the quadratic, and the quadratic helps you memorize this. So
Okay.
we don't need the quadratic formula. I only wrote it to point out the similarities between that and the quadratic formula. And so if you know the quadratic, you always can figure this out. Now,
Okay.
for this particular quadratic, what is minus b over 2a?
Minus b is negative 3 over 2a, which is negative 2/20.
Which is negative 1/10.
Yeah.
What's that equal to?
It is
How do you divide by a fraction?
uh
Flip and multiply.
okay.
So to divide by 1/10, I'm going to multiply minus 3 by minus 10 over 1, which gives me 30.
Okay.
So 3 divided by 1/10 is 30. And it's positive because it's negative divided by negative.
Yeah.
So that's where that occurs, is when x equals 30. That's where this peak occurs, right here.
Okay.
Now, if we want to know what the y value, what's the actual height of the ball, then I got to plug 30 into this equation to come up with y. So the y coordinate of the vertex is a little harder to get, but I'll just plug it straight in here. 30 squared plus 3 times 30 plus 5. Now, let's see if I can do this math in my head. This is minus 900 divided by 20, which is
that's minus 45.
Minus 45 plus 90 plus 5 equal to 50. So if I go back to my picture, that's 50.
Okay.
Okay. So I've solved for the maximum occurs when x is 30 and y is 50. So let me erase all of this. And the other thing they wanted to know is the height of the person throwing the ball, basically, or shoulder length. In other words, this would represent the height that the ball was at x equals 0. What is that?
Isn't that 5?
Uh-huh. In other words, the y-intercept is always that number, because the y-intercept occurs when x is equal to 0, and when x equals 0, both the first two terms of a quadratic disappear.
Okay.
Anytime you have a quadratic, or for that matter a cubic, anything that has the same variable and then a constant. Well, the moment you make that variable 0, all terms with it disappear and the constant is the y-intercept. So
Okay.
on this, that's definitely 5.
Okay.
Now, what else do
And then they,
you want to know?
does changing this value change the coordinates of the maximum height of the ball?
Changing which value? 5?
Yeah, I think so.
Well, when, what do you think?
Well, yeah, I think it would, because then the maximum height of the ball would be raised by whatever value that is.
Yeah, you would think that would be true, and it is true. In other words, if I change that, then the vertex doesn't change the vertex. In other words, it doesn't change the maximum height that occurs when x is equal to 30. The x-coordinate of the vertex is still 30. But the y-coordinate of the vertex is going to be 30 plugged into there. And obviously, if 5 becomes 6, then the y-coordinate is affected. So the y-coordinate was 50 before, but if the ball is thrown from a height of 10, then the y-coordinate would be 60.
Okay.
Excuse me, 55.
Yeah.
It would be 5 feet higher than it was. So the answer is yes, because it changes the x, more specifically, it changes the y-coordinate of the vertex.
Okay.
Typically, when you see a problem that is projectile motion, which anytime you throw something into the air, it follows the equations of projectile motion. And that ends up being a quadratic always. And frequently, instead of x, this is t. Because really, most projectile motions are a function of time, not some arbitrary x. In other words, if I make this t instead of x, and that's time. When time is 0, the ball's at 5 feet. When time is at 30 seconds, the ball's at 50 feet. And they would want to know, well, what time does the ball hit the ground? Do they ask that on this question?
No, not on this question.
Well, let's do that, because you're going to get asked that. It's just, just a matter of time before you get the projectile motion equation.
Yeah.
Well, how would I figure that out? Remember what y is. Y is the height of the ball at any value for x.
Okay.
What's the height of the ball when it hits the ground?
Y is equal to 0?
Yeah, that's the key. And now solve for x, and you'll figure out what value of x creates a y of 0.
Okay.
Okay. And you'll actually, in other words, we need to solve this quadratic. Well, how about we multiply everything by 20 to start with?
Yeah.
In fact, let's multiply everything by minus 20.
Yeah, because that'll take out
this minus 60x minus 100.
Okay.
That's equal to 0. And I can multiply by any number I want, both sides, because no matter what I multiply by 0, it stays 0. So all I've done is turn that complicated looking quadratic into a quadratic we can deal with a little bit more.
Yeah.
Now, not that this is the easiest thing to factor, but let's see. What factors of 100 subtract to 60? Well, let's see. Not 100. Let's go through the factors of 100. 101. That doesn't subtract to 60. 50 and 2. 25 and 4. No.
20 and 5. Um,
10 and
10.
10. I don't know that there are any factors of 100 that subtract to 60. So
Okay.
in order to solve this quadratic, look, I mean, I can't think of any.
No.
In fact, there can't really be any. Because if 101 are two factors, they subtract to be 99, well, there's not going to be a factor bigger than 50, right?
Yeah.
And if it's 50 times 2, those do not subtract to be 60 either.
Okay.
So there's no way I'm finding two factors of 100 that subtract to 60, which means I have to use the quadratic formula.
Okay.
Okay? And I actually could have used the quadratic formula on the original equation just as easy as I can use it here. Maybe easier. These numbers are a little smaller. But this fractional number is going to make the arithmetic a little more difficult.
Yeah.
But probably not as difficult as this arithmetic's going to be. In other words, if we try to solve this using the quadratic formula, well, before I do that, since they didn't ask you this question, let's not spend our time doing this.
Okay.
Let's go to the next one they asked you. But that's how you would solve for this value.
Okay.
I hate this program. If you forget you're in erase mode, it erases everything.
Huh.
Notice that this quadratic is going to produce two solutions, right?
Yeah.
One will be positive, one will be negative. Well, if I extend that parabola back to there, there's the negative answer, there's the positive answer.
Okay.
Now the negative answer is never applicable because this is always t, not x. And times don't go negative. There's no such thing as a negative time.
Mm-hmm.
But it explains the math. In other words, because the thing was thrown from a height of 5 feet, it never was on the ground until the very end. But even still, this is going to produce a positive and a negative x value. And you're going to discard the negative one because we're not looking for that point right there.
Okay.
That point, the ball was never at this point. But the ball does get to this point over here.
Yeah. Well, I understand.
All right. So did we finish that problem?
Yes.
All right. Let's go to a new problem rather than going through the quadratic formula on those big numbers.
Mm-hmm. Okay. The next one is sketching a graph of the function and identifying any asymptotes.
Okay.
So this one is f of x equals natural log of x minus 4.
The best way to do these is to know what your parent function looks like. What's the parent function?
Okay. Of a natural log?
No, what's the parent function of this? In other words, what we're looking at is a transformation of the parent function.
Wouldn't the parent function be lnx?
Yes. And that looks like, you want to have a pretty good idea of what your 10 elementary functions look like. And that's natural log of x. That's y equals natural log of x.
And doesn't it always go through the point 0, 1?
It does, regardless of what base it is. In other words, even if it was y equal log base 7 of x, it's going to look very much like this and go through this exact same point. In other words, the log of 1 is always 0, whether it's natural log or log base 17.
Okay.
Log base 17 of 1, that's 0. Log base natural log of 1, that's 0. Common log of 1, that's 0.
Okay.
Okay? So whenever that's why all of the log functions go through that same point. So
Okay.
the question is how does this differ from what they gave you? Can I define f of x in terms of some transformation of g of x?
Doesn't it shift right to the right 4 units?
Yeah. What I'm really talking about doing though is f of x is actually equal to g of x minus 4, correct?
Yeah.
And so g of x minus 4 would be the natural log of x minus 4, and that's f of x. Now, if I examine that, I know exactly what's happening to this function. What is it?
It's shifting right 4 units on the x-axis.
Correct. Which means
Okay.
if I draw it in red, this point becomes what?
0, 5.
No, remember we're going to the right on the x-axis. So that point goes to 4.
Oh, 4, comma.
Hold on,
0.
just a second. Let's back
No,
up. Let's back up. Let's back up. That's not 0, 1. It's 1,
1, 0. Yeah.
and then I'm moving it 4 units to the right, so it becomes,
So it becomes
5,
5,
0.
Okay.
And now my new function looks like that. And the parent function has a vertical asymptote, right? What's the equation of the parent function's vertical asymptote? What's the equation of that red dotted line?
X equals 0.
Yeah. What's the equation of the dotted line that's going to go with my translated?
X equals 4.
Yep.
Okay.
And that's the only asymptote you have on this function. Even though when you look at the natural log function, it looks a lot like there could be a horizontal asymptote at the top. It is, in other words, it's so flat. If I draw most natural log or any kind of log, it looks like this, and it looks so flat that it looks like there could be a horizontal asymptote there. But it is not. In other words, as we go to infinity, that goes to infinity vertically also.
Okay.
In other words, the end behavior as x goes to infinity is y goes to infinity. This is called one of the flattest functions you will ever see. And what that means is I've got to go 2 miles on the x-axis to go up 12 inches on the y-axis.
Yeah.
That's the relationship. That's how flat this thing. In other words, that's how slow growing this is. That I got to go 2 miles in this direction in order to go up by 12 inches.
Okay.
So this is one flat function. It is also the inverse of the exponential function. It's a perfect inverse. The exponential function, y being e to the x, its inverse function being y equal natural log of x. And as all inverse functions, they are reflections about the line y equal x.
Okay. Okay.
Just don't get confused that these are the same thing. They're not. In other words, I know I dealt with this confusion a lot in my life. If I want to write that logarithmically, then it would be the natural log of y equals x. These two are the same.
Okay.
Because all I did was take the natural log of both sides. These two up here are not the same. They're inverses of one another. Notice
Okay.
the second equation on the left is not the same as the inverse equation.
Okay.
Okay?
All right.
So that's one thing to keep in mind, is that exponential equations are not inverses of all log equations. You can write these two and they're identical. Those two are identical to one another. Whereas these two up here are not, they're inverses of one another.
Okay.
All right.
Okay.
What else?
Kind of similar. It is negative log of x minus 6.
The minus 6 being inside the argument or outside the argument?
I think outside. No parentheses.
Okay. So the parent function, if I call that f of x, parent function, which I got to call something else, is common log of x.
Yeah.
Just like the other one. In fact, if I gave you just the graph, you wouldn't be able to distinguish this from the other one.
Yeah, okay.
Not if I gave them to you one at a time without a grid. In other words, if I just draw it like this, you don't know if that's natural log or common log or log base 21.
Okay.
Okay? We got two things that are going on. And to me, the way you want to do all transformations is you want to figure out how f of x relates to g of x. In other words, f of x is what g of x? Well, for starters, it's minus g of x minus 6, right?
Yeah.
Okay.
Okay.
Now that I know how f of x relates to g of x, I know how to handle that. What two things are going on here?
It is
The initial negative sign does what?
it reflects it over the x-axis?
Yes, it's a vertical reflection. The way I like to think of all these transformations is there are 3 vertical transformations and there are 3 horizontal transformations. All of the vertical transformations, everything is done outside of the parent function. Notice that negative sign is outside of g of x and the minus 6 is outside of g of x. So both of these are vertical. If I had something like f of x ended up being equal to g of minus x, well, now that negative sign is inside the function, therefore it's got to be horizontal reflection. Okay? So to me, that's the best way to memorize your transformations and reflections is there's 3 vertical, and a vertical reflection means reflecting it over the x-axis. So, and you always do your reflections first. Order does not matter except reflections have to be done first. It does matter with regards to reflections. If you have strictly translations or shifts, doesn't matter what order you do. But if there's a reflection involved, whether it's inside or outside the function, you have to do those first.
Okay.
So if I do just this in blue, I'm going to reflect it over the x-axis, and it's going to look like that. Now let's do the minus 6.
Doesn't that just shift it left 6 units?
No, that's outside the function.
Oh, that shifts it down.
Got to be vertical, right?
Yeah.
In other words, if I wanted a shift left or right, I would have to write it like this. That would be a shift to the right of 6.
Yeah.
And that's inside the parentheses. That means it's inside the function, it's horizontal. What we're dealing with is outside the function, got to be vertical. You're correct, it's got to be down 6. So the only reference point I have is that one. Let's move that down 6. What are its new coordinates?
Its new coordinates would be 1, comma, -6.
And I would draw the blue line through the new coordinates. So
Okay.
my final line looks something like that.
Okay.
Now, what's the vertical asymptote on the original function?
0, x equals 0.
What is it on my final f of x?
Isn't it still x equals 0?
Yeah, because everything I did was a vertical move. In other words, I did a vertical reflection, which didn't change the vertical asymptote, and I did a vertical shift, which did not change the vertical asymptote. Had I done horizontal stuff, then I got to move my vertical asymptote also.
Okay.
Okay? So, and that's the case with all asymptotes. If you have horizontal asymptotes, then vertical stuff changes the asymptotes. But in this case, where we have nothing but vertical asymptotes, then vertical stuff does not affect that. So we still have one, but it's the same as the parent function, x equals 0.
Oh, okay.
Okay? What else you got?
The next one is, I know how to do that. Solve the system graphically. Okay, so this one. In exercise 4 and 6, solve the system graphically.
Okay.
So this one is y minus natural log of x equals 12. And then 7x minus 2y plus 11 equals 6, equals -6.
Okay.
And it wants to solve these systems graphically.
Well, if I can, this bottom one, that's a linear equation, right?
Yeah.
In other words, I can put that in y equal mx plus b format.
Mm-hmm.
In fact, let's do it. I'm going to move the y to the other side. I'm going to move the 6 to the left, and I'm going to end up with 2y equals 7x plus 17. Divide everything by 2, and I get y equals 7 halves x plus 17 halves. So I know how to graph that.
That's the same as the original linear function?
What's that?
And that's the same as the original linear function?
Yeah. In other words, this is the same as this. All I did was algebraically manipulate it. I know it's linear because it's got an x and a y in it. There's no squared term. It's not x and y squared, which would be a parabola. It's not x squared and y squared, which would be a hyperbola. It's just x and y, which makes it linear. Means a straight
Okay.
line. It's got a slope of 7 halves. There's approximately what it looks like. If you had a proper sheet of graphing paper, you'd be able to graph it exactly, okay?
Uh-huh.
And the question is the top one. Well, if I move that natural log over to the right, I get this, right?
Okay.
Well, I know how to graph that. What is that? What kind of translation of the natural log function is that?
A vertical shift upwards of 12?
Yeah, and that's a pretty good vertical shift. In other words, I'll draw the parent function, and now in red, I'll draw the shifted function. So the shifted function is going to look something like that. And it looks like it could cross it in 2 places. So we might actually have 2 solutions. I don't know. Let's see. I don't think we can solve this algebraically, but it didn't ask you to, did it? It asked
No, it just said
you to
solve it
solve
graphically.
graphically. Well, the way to do that is, what kind of calculator do you have, Nick?
A TI-84 plus, I think.
Okay. So that's y sub 1. That's y sub 2.
Okay.
Graph it. You'll get 2 lines, and then find the intersection point. Those are your 2 solutions.
Okay, cool.
Assuming there are 2, I don't see how there could only be 1. I could picture if you had a line and a log function not intersecting at all. In other words, here's my line and there's my log function. Those don't intersect. So there isn't necessarily a solution when you have a log function and a linear function. But if my log function has been shifted up, then it looks like it could either be tangent to that line at some single point, or it's probably going to go through and you're going to have 2 intersection points.
Okay.
And I suspect that that's the case, because 17 halves is 8.5. We're shifting up 12, so we're definitely going to be up where my red is.
Okay.
Which means there's going to be 2 intersection points, because that one there for sure, and then since the line keeps going up to the right and the red curves around, there's going to be another one up there.
Okay.
And your calculator will show you both points of intersection, and you just have to find them both.
Okay.
And you would want the x and y coordinate for both.
Okay.
Because when it gives you 2 equations and 2 variables and it says solve the system of equations, it wants you to solve for both x and y.
Okay. Okay. All right. The next one is determining the right hand and left hand behavior of the graph of the function, and then they want us to sketch the graph.
Okay.
So it is h of t equals -3/4 t to the 5th plus 2t. 2t squared, sorry. And that's it.
And they want what?
The right hand and left hand behavior of the graph, and then they want to sketch it.
Okay. Well, let's talk about the end behavior first. The end behavior of any function is only dependent on its highest degree variable.
Okay.
So I can ignore the 2t squared for the moment and focus on what happens to that as t goes to negative and positive infinity. Well, what happens when it goes to negative infinity? What happens to my term that I've circled?
As t goes to negative infinity.
And the best way to think about it is to substitute negative infinity for t. In other words, what I really have is -3/4 times negative infinity to the 5th power.
Okay.
When you take negative infinity and square it or take it to an even power, it becomes positive infinity.
Yeah.
When you take it to an odd power, it stays negative infinity.
Okay.
So this part here is still negative infinity multiplied by a negative sign there. That means it's positive infinity.
Oh, okay.
So this curve's going to come down from that point right there.
Yes.
It's not going to come up from here. In other words, the bottom would be the end behavior would be negative infinity as x goes to negative infinity. But in our function, the end behavior as x goes to negative infinity is y, or h of t, comes from positive infinity. So if I could figure out my zeros of this graph, you sure it's t to the fifth and t squared?
Yes.
Okay. Well, let's go back and figure out what the right-hand end behavior is by substituting positive infinity in there.
Okay.
What's the right-hand end behavior?
You substitute positive infinity, it goes to negative?
Yeah. So it's coming up from there at the end of it. So this is my left-hand end behavior, this is my right-hand end behavior.
Okay.
If I could only figure out my zeros, I can draw the graph. Well, let's see if we can figure out our zeros.
Okay.
Well, the first thing, I can factor out t squared.
Mm-hmm.
So this is equal to t squared times minus
negative
3/4 t cubed
to the third
plus 2.
Plus 2. Okay.
Okay. Now, I know I'm going to have 5 zeros, right?
Yes.
I would expect to have 5 zeros. Some of them might be the same.
Like the t squared, wouldn't that be a double zero?
At 0. So
at 0.
Let's list them. I got t equals 0 of multiplicity 2. And then if I solve this part over here, I get minus 3/4 t cubed plus 2 equals 0, so equals minus 2. Get rid of the minus signs, multiply both sides by 4/3, I get t cubed equals 8/3.
Okay.
T is equal to the cube root of 8, which is 2, over the cube root of 3, which I can write like that.
Okay.
Which is an interesting problem in and of itself. In other words, that also needs to be rationalized. Notice that that answer has an irrational denominator in it.
Okay.
Okay. The way to rationalize that is to multiply top and bottom by 3 to the 2/3.
Okay.
Notice what that'll give me in the bottom. 3.
Okay.
So my answer is 2 times 3 to the 2/3 is the same as the cube root of 3 squared. That's what 3 to the 2/3 means.
Okay.
And that becomes 3. So 3 squared is 9. So my other value for t is 2 cube root of 9 over 3. And that's plus only.
Okay.
And there are 3 of those. So that has multiplicity of 3.
Okay.
Let me think for a minute here before I go on. Okay, multiplicity. Okay, so there's only 2 zeros on this thing. One is right there, and the other is whatever the heck that is. Let's see if I can figure out a close approximation for that. That's about 2. 2 times 2 is 4 over 3. So that's in this neighborhood here. We'll call it 2 cube root of 9 over 3. Okay, so there's another 0, and there's 3 of those. Now, here's the deal about multiplicity. If you have an even multiplicity, it does not go through the horizontal axis. It kisses off of it and goes back up. If you have odd multiplicity, it goes through the axis. Okay? So I know that if I'm coming down from here, I'm not going through there. I'm going to kiss and come back up, but then I'm going through that one.
Okay.
It might look something like that. Now, if you like, I can pull up Wolfram Alpha and graph this thing and see if it looks something like that. Let's do it just for the heck of it, just to make sure. You could do this on your calculator also, but I can't see it then. So let me pull up Wolfram Alpha, which is an excellent graphing calculator, and put in this function. Can you read the function to me again?
Yes.
What is it?
The function is negative 3/4 t to the 5th.
Negative 3 divided by 4, and I'm going to use x.
X to the 5th. Plus 2x squared.
Plus 2x squared. And the beauty of Wolfram Alpha is that it shows you what you put in. Like right there is my input. Okay. And then it gives you 2 graphs, one being just a scaled version of the other. Yeah, it does kind of do. In other words, my graph looked like, hold on. Here, let me put that on the left, and I'll show you my graph on the right. If you look at the bigger scale, you can see the end behavior we got right.
Okay.
Look at the zoomed in scale, we also got that right. In other words, it goes through and bounces off of x equals 0, goes back up, and comes back and goes through that point, which is at about 1.4. And the other beautiful thing about Wolfram Alpha is it gives you your roots.
Yeah, okay.
Your 0.
Oh, wow.
Notice how it gave us our 0. I've always found this fascinating.
Huh.
Notice it gave us our 0 with an irrational denominator.
Wow.
Cube root of 3 is irrational. Now, what's up with that? Well, they're the same numbers. In other words, they're not different numbers. If I go over to a new page and I say 1 over square root of 2, well, after I rationalize it, it becomes square root of 2 over 2. If I put that in a calculator, I'll get exactly the same numbers if I put that in a calculator.
Okay.
Effectively, you don't change the number, you merely, I've always tried to figure out why that's a rule in math, and this is making me rethink whether it actually is a rule. I'm not sure that it is more than just a convention. And to me, the reason for it is, how do you divide something up? In other words, I can divide a piece of pie up into 3 pieces, right?
Yeah.
I can divide a piece of pie up into 5 pieces. How do I divide it up into the square root of 2 pieces? Can't do it conceptually.
No.
The process of division requires you to think of it, at least, in terms of dividing by a rational number. And so that's why I've always thought that math doesn't like giving you irrational denominators, or for that matter, imaginary denominators, because you can't divide something up by that amount. And yet, here we have one of the greatest math sites in the world, Wolfram Alpha, and they're giving us answers with irrational denominators. So they don't care. And I've always felt like it didn't matter either. That's as valid of a number as it would be if I rationalized it.
Yeah.
So that's how you do that problem. But the key for these kind of problems is recognizing the multiplicity of your zeros and knowing that if you have odd multiplicity, it passes through the x-axis. If you have even multiplicity, it bounces or kisses the x-axis only. Now, it looks like these aren't the same, right?
Yeah.
But they are. If you zoom way in here, you see this hump. You can barely see it on the zoomed out version.
Okay, yeah.
This is
yeah.
20 times zoomed in. And this little tiny hump here shows up as this big hump here. And this is the way I drew it.
Okay.
Okay. So it's all you have to do is identify the zeros, identify their multiplicity, then and their end behavior. And once you do that, you can pretty much graph any function. In other words, the zeros and the end behavior allowed me to graph that thing. Because there was only 2 zeros, and I knew it had to bounce off that one, and it had to go through that one. So the basic shape of the curve, you can graph real easily by just finding the zeros, their multiplicity, and their end behavior.
Okay.
Okay. Nick, I actually have a 6 o'clock I got to go to, so I'm going to have to let you go.
Yeah, no worries. Thank you. Oh, scheduling a Saturday appointment?
Yeah. When would you like it? What time?
Hey, Pickle?
Yeah, what time would you like to schedule a Saturday appointment?
Well, I'm just saying, you just got an email that you actually are open Saturday morning if you want to change it.
I don't have Saturday morning?
No, you're not on the Meals on Wheels shift in the morning. So if you want to do...
I'm not open Saturday morning. I have an in-person at 10.
Oh, okay.
But
we could do...
Yeah, afternoon would work better. That 10 o'clock might get postponed because we're supposed to have snow and super cold weather that day. But
yeah, so...
Okay, so how about 4 p.m.? Is that okay?
4 p.m. works great.
Okay, so can we cancel the Monday one then, and we'll do this one at 4?
Yeah, let's do that.
Okay.
Hold on a minute.
And then I was going to tell you something else, because I don't know if Nicholas told you, but good news is, did you tell him what your grade is?
Oh, yeah, I'm at a B in math.
Oh, very good.
He has an 80.17,
Oh.
so we went from an F all the way to a B.
And I just need to get a B on the final to keep it.
So thank you so much for your help. You said it and
I don't deserve the credit as much as Nick does because he's the one that's been putting in all the time. And that's really what it comes down to. So this 5 o'clock on Monday you want me to cancel, right? On Monday?
Yeah, we need to cancel the Monday one and stick with the 4 o'clock on Saturday afternoon.
Let me do that. That's done. And I will talk to you at 4 on Saturday, Nick.
Okay, cool. Thank you, Mr. Cohen.
I'm bringing your grade up. That's terrific.
Thank you.
Thank you for all your help.
You're welcome. Bye.
Bye-bye.
Bye, Nick.